So we are recording. This recording will discuss Chebyshev's theorem and range of data and using standard deviation to explore the range. Now, when we obtained standard deviation, it was a multi-step process to get standard deviation. We had to take the data, find the mean of the data, find the difference of the mean and each data point, square that, get the sum of the squares, divide the sum of the squared by the number of data points or one less than the number of data points, taking the square root. That's the steps to determining the standard deviation. However, sometimes you might just need to get an estimate of the standard deviation, an estimate of the standard deviation. So that's what the range rule of thumb comes in. The range rule of thumb allows us to just get an estimate. So if we need quick calculations, this is a good time and a good way to just estimate what your standard deviation will be. And the range rule of thumb is if you take the range and divide it by 4, that should give you an approximation of your standard deviation. Won't be exact, but it's just an approximation. So if you want to get pretty precise with your standard deviation, you want to take all the steps that, to get the mean, get the difference, all of that. But if you just want to get an estimate of the range, of the standard deviation, take the range of the data and divide it by 4. So that's what range rule of thumb indicates. So that's just something, actually, I should have put that in with the last unit, but I think I was running short on time. So just to kind of show you what we're talking about. So we have the sample data 5, 8, 8, 9, 10, 12, 13. So if you calculate the sample standard deviation, it is about 2.7. If you want, you can actually calculate it, but I can even show you how I calculated it, but it's about 2.7. Just to show what we're talking about with the range, for this same data, let me change colors. Oops. The range is going to be the largest value minus the smallest value. In this case, 8. Just trying to make that print a little larger, but I guess I can't. So if the range is 8, an approximation, the standard deviation should be approximately, standard deviation, is approximately 8 divided by 4, which is 2. So the actual standard deviation is 2.7. But if you use the range rule of thumb, it is about, you'll see this 2. So that's why we could use that to kind of get a quick estimate. It's not going to be exact. That's why we call it estimate. But how we could get a estimate of the range, of the standard deviation. If you have the range, you can estimate the standard deviation by simply dividing by 4. The range divided by 4 will estimate the standard deviation. That's what the range rule of thumb is. So any questions about like the range rule of thumb? Okay. All right. So like I say, so for those when you have to do some quick estimations, if you have to quickly estimate standard deviation, get the range divided by 4. But my main focus for today is what's called Chebyshev's theorem. Chebyshev's theorem. And this is the technical definition. the proportions of values from any data set that fall within K standard deviations of the mean will be at least 1 minus 1 divided by K squared, where K is a number greater than 1. So what that means in regular language, if I want to know, and this is kind of what this chart tells us down here, if I want to know what percentage of my data is within 2 standard deviations. So in other words, if I have a mean of, if my mean is 10 and the standard deviation is 2. So let me annotate that up here. So if my mean is 10 and the standard deviation is 2, within 2 standard deviations of that mean. So move this up a little bit. So if I say the mean plus 2 standard deviations, that'll be the upper boundary. And then if I take away 2 standard deviations, this means that 75% of all data within that set will fall between 6 and 14. So if I was able to list all of the data points, 75% of them. So I have some data, I don't even know how many points of data I have, but for that data, if the mean is 10 and the standard deviation was 2, that means 75% of my data is between 6 and 14. So 75% of the data. So if I had 100 pieces of data, and like I say, the mean is 10, the standard deviation is 2, 75, at least 75 pieces of data, or 75% of the data, is in between 6 and 14. Or for 3 standard deviations, because that means I would go 2 units higher. So 3 standard deviations. Oops, I went 10 plus 3 times 2, that's 16. And 10 minus 3 times 2, that's 4. So that's 3 standard deviations. According to Chebyshev's theorem, 88.89% of all of my data will fall between 6 and 14. So Chebyshev's theorem gives us, or allows us, to determine what percentage of the data will fall within a certain range. What percentage of the data will fall within a certain range? So that's what Chebyshev's theorem entails. What percentage of the data will fall within a certain range? So I'm going to have a few examples. Let's try some. Oops. Or this is kind of another way of just looking at it visually. Because if my mean, I forgot I had this. I looked hard for this. So if my mean is, I circled the mean, it's at the bottom, X bar. If I go 2 standard deviations away, so everything, so this is 2 standard deviations. So 2 standard deviations, at least 75% of the data has to be within 2 standard deviations of the mean. That's Chebyshev's theorem. Or about 89% or 88.89% of the data is within 3 standard deviations. So remember, standard deviation is just the average distance from the mean. So Chebyshev's theorem tells us that 75% of all data, of all the data in the set, will be within 2 standard deviations of the mean. 88.89% of all the data will be within 3 standard deviations of a mean. So that's what Chebyshev's theorem tells us. What is the range of the data? So I want to know where the 75% of the data lie. Well, 75% of the data is between 2 standard deviations. Let's kind of look at some practical examples. I have a couple here, and then I have 2 here, and I have like 4 or 5, and somewhere else I want to go. Well, we'll go through some of those 4 or 5. All right, let's click. Okay, so the mean price of houses in a certain neighborhood is $50,000, and the standard deviation is $10,000. Find the price range for which at least 75% of the houses will sell. So the mean of the house price is $50,000. And on average, the average distance from the mean is $10,000. Let me kind of back up real quick to something in our chart. 75% of the data is 2 standard deviations from the mean. So according to Chebyshev, 75% of data is 2 standard deviations from mean. So we can determine what is the range? What is the low end and the high end? Because we want to say at least 75% of the houses sold from here to here. So to get the low end, if we take the mean, or the low end, I'm sorry, and we're going to subtract 2 standard deviations. So 50,000 minus 2 times 10,000, that's 30,000. And then to get the high end, so if we look within 2 standard deviations of the mean, this tells us that 75% of the houses sold for $30,000 to $70,000. So the price range for which at least 75% of the houses sold was from $30,000 to $70,000. What I'm going to do, I'm going to pause the recording. Okay, resuming recording. So, like I said, we were able to get the price range for at least 75% of the houses sold. Let me clear these out. Okay, let's try a slightly different one. A survey of local companies found that the mean amount of travel allowances for executives was 25 cents, or 25 cents per mile. The standard deviation was 2 cents. Using Chebyshev's theorem, find the minimum percentage of data values that fall between 20 cents and 30 cents. Okay. So but here's the thing. We know the standard deviation, but we don't know, let me type this in. We want to know, well, how many standard deviations? Standard deviations away from the mean is 20 cents and 30 cents. So the first thing, because we need to know how many standard deviations. So what we can determine, oops, is that the low value is 20 cents, 20 cents minus 25 cents. So that means that they were 5 cents away, right? But then if we take that, oops, yes, it is. Then if you divide that difference by the standard deviation, you'll see that this was technically like 2.5 units below, 2.5 standard deviations. Let me put the standard deviations. So 2.5 standard deviations. So the low end is 2.5 standard deviations below the mean. The high end, and if you wanted to calculate it, it'd still be the same thing. 30, keep forgetting to write this change. And then, like I said, if you just divide 2.5. So either way it goes, 2.5 standard deviations. So now that we know how many standard deviations, 2.5. So it's 2.5 standard deviations from the mean. Let's do this. So, but we could figure out the percentage. So if it's 2.5 standard deviations from the mean, K is the number of standard deviations, 2.5. So Chebyshev's theorem, this is where it's going to be a little harder for me to try to write this part out, is 1 minus 1 divided by 2.5 squared. And then we have to actually calculate that out. But if you calculate that out, you get 84, 0.84. So that's our percentage. Because we wanted to know the minimum percentage of data values that fell between 20 cent and 30 cent. 84% of the data values are between 20 cent between 20 cent and 30 cent. Oops. So that is Chebyshev's theorem. So Chebyshev just explores the relationship between number of standard deviations and percentage of data that'll fall so many standard deviations away, K number of standard deviations away. All right. right, let me, I actually want to record this part. That's a good question about the formula. So this technically is the Chebyshev's formula right here. That's why I say I was having a problem trying to get it in that same format when you're typing something in. So once you know the number of standard deviations, you know, you want to know what percentage of data, the minimum, or the percentage of data that falls within 7 standard deviations. I just picked a random number. K, you use 7 in place of K. So this is the actual formula. 1 minus 1 divided by K squared. So that is Chebyshev's theorem. How he got to the theorem is, I'll be honest, that's not something that we necessarily do in this class. That is one of the separations between this class and AP Stats. And literally, because I considered making this an AP Stats class, and I was looking at one of the differences, and that's one of the main differences is proving the formula. If you would like, later on, I could create a video that shows the proof of the formula, but I kind of wouldn't want to do it in the class as to where this exactly comes from, but it is based off of rational functions. It is definitely based off rational functions and the concept of limits. So if anybody took pre-calculus, especially you start thinking about rational functions and limits and approaching and all of that, that's where it all comes from. Not all comes from, but a good portion of why that is the formula. So I'm making a little note for myself. I'll do that Friday afternoon. Video proof. Chebyshev. Very weird thing to spell out to Chebyshev. Okay. So I do want to look at a few more, couple more examples. Oh, wait, I didn't mean to click that. That's the wrong thing. I didn't mean to click that. Didn't mean to do that. I meant to go back into the Google Classroom. And I want to look at some of these questions. I want to actually work through several, it's about 2 of them I want to work through together to kind of get a little further explanation about Chebyshev, get a little further practice. Unfortunately, I had to do all this as a PDF because that's, yeah, just had to be a PDF. All right, I'm going to look at just a couple of these questions. So for the first question, as a matter of fact, well, nah, I can stick it like that. So the first question, I want to look at numbers 1 and then numbers 1 and 3 are the 2 that I want to look at. Well, 1 and 3. First, using number 1. Number 1, using Chebyshev's theorem, solve these problems for a distribution with a mean of 80 and a standard deviation of 10. At least what percentage of values will fall between 60 and 100? So what percentage of values will fall between 60 and 100? Excuse me, and 100. So number 1, first thing, how many standard deviations is that? How many standard deviations? How many standard deviations is that? So from 60 to 100, but you have a mean of 80 and the standard deviation of is 10. So for part A, That is 2 standard deviations. Because if you do 80, the first standard deviation, add 10 is 90. The second standard deviation is 100. Or if you're at 80, subtract 1 standard deviation is 70, subtract 2 is 60. So that's 2 standard deviations. So since it is exactly 2 standard deviations, to figure out the percentage is 1 minus 1 divided by 2 squared. Let's see if I can move this a little bit. So if we calculate that out, we get 75 or 75%. So 75% of all the data should be within 60 and 100. So 75% of the data should be within 65 and 100. Now for B, because we're counting up to 95, so we got to count 1 full standard deviation and half of a standard deviation. So that's 1.5 standard deviations. Or you could look at it and say 95 minus 80 is 15. 95 minus 80 is 15. 15 divided by 10, that's 1.5 standard deviations. So the percentage of data that's 1.5 standard deviations away is 1 minus 1 divided by 1.5 squared. And that is equal to, let me actually calculate that out. About approximately 56%. It's technically like 55.5 repeating. I just kind of round it. Any questions about that first one? And just to let you know, the more standard deviations, the more of the data that will fall within that range. More standard deviations, the more data will fall within that range. Okay. All right. So that's question number 1. Let's take a look at question 3. Time spent online. I find this funny because you could tell that's very old data. That was pre-COVID because that has changed for many, 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 many Americans like myself. So at the time they did this data, Americans spent an average of 3 hours per day online. If the standard deviation is 32 minutes, find a range that is at least 88.89% of the data will lie. Okay, so let's start here. Mean. Wait, before I even get there, have to be very cautious about some of these questions I always like to call this like a standardized test question, where they have this one little trick in there. They give you different units. They tell you they spend 3 hours, but the standard deviation is 32 minutes. When you're operating, you want to operate within the same units. So really, the mean is 180 minutes. I'm gonna get rid of these up top just so I can have a little more space. So the mean is 180. Oop, mean is 180 minutes. So we got the mean. We know the standard deviation. We know the standard deviation is 32. They may need to keep deleting that. But the question is, what is the range that's going to be 88.89% of the data will lie? Well, according to Chebyshev's theorem, the quick let me do just a quick recap. Oh. 88.89% of the 88.89% of the data is 3 standard deviations. 3 standard deviations. So we want to be 3 standard deviations from the mean. So we want 3 standard deviations away. So the range for the low end so 180 minus 3 times 32. So 84 minutes. But the high end, because it's 3 standard deviations, and that is 276 minutes. So the range that at least 88.89% of the data will lie between 84 minutes and 276 minutes. So like I say, Chebyshev's theorem just talks about how everything is spaced out. It's just about variation and spacing of data, using the standard deviations to get the spacing of the data. Okay. So technically, this is your first assignment. There's only 5 questions. Actually, it's covered 2 of them. Since I was making this 3rd quarter, and like I say, because it was just really about a matter of having time to grade everything. That's why I didn't assign anything new this week. Let me stop recording.